Hey everybody, this is going to be a quick roll through energy level diagrams in this video. So previously we had talked about the introduction to quantum mechanics and the idea that atoms are made up of electron clouds, and that those clouds were known as energy levels, and that they all had different shapes. And we knew that there were S, P, D, and F type orbitals. Right, and each of those had their own different lobes to them, which held electrons. Okay, and this is in comparison to the Bohr diagram, where in the Bohr diagram we had those circular rings, and each ring could hold an electron. Well, what we're saying is that's not an efficient model anymore. So we have this model, which is being supported with current research. So the goal of this lesson is going to be to define the terms here: the Aufbau principle, the Hund rule, and the Pauli-Exclusion principle as we build energy level diagrams, and then we will tie that into electron configurations in a second part to this video. So energy level diagrams compare the relative energy and stability of each orbital. Okay, so what relative means is that there is no absolute value to it. So we're just comparing something is higher or lower in this case in terms of the orbitals. So just make a note of that as we go. That's why you won't see numbers here. So one of the explanations is that the distance from the nucleus determines its energy level. I'm going to put a little asterisk here. That's partly true. There's a couple of different factors that affect that as well, such as the electron density. Okay, so we'll just put that there. But in general, okay, you can see the ranking of orbitals here in terms of energy. This is the order that electrons fill them. So the s orbital has the lowest amount of energy, then it goes p, d, and f has the most amount of energy at this point in time. So what that means is an electron in an s orbital is unlikely to react relative to an electron in an f orbital. So f orbit electrons are much more reactive than orbitals. So in terms of how do we know what orbit an electron is in? Given an atom? Well, we do that with a couple of different patterns that have been developed over time. The first one that you see here is known as the Madelung rule or the staircase pattern. So in the textbook, if you have Nelson Chemistry 12, you can see the pattern is here. This tells us the order that electrons are placed into, because essentially every atom begins with a nucleus, and then electrons are added to that in order of energy level. Now, with a Bohr diagram, just to quickly make a note, okay, if I had a 10 electron atom or ion, the first 2 electrons go in the first energy level, and then the next 8 go in the second, because the second energy level can hold 8 electrons. Well, what we're saying now is that's incorrect. Evidence suggests that it doesn't happen. Rather, this happens where the energy levels are filled, but based on orbital, not energy level. So we don't just say that the electrons go in the first energy level. They get split between the s, p, d, and f orbital. So as a quick recap, the s orbitals can hold 2 electrons each. The p orbitals can hold 6. The d orbitals can hold 10. And the f orbital can hold 14. Right? And it depends on the energy level there. So the first energy level only has an s orbital. The second energy level has s and 2p, which is why it can hold 8 altogether. So there. The third energy level has a d orbital, which means it can hold up to 18 electrons, and then so on. And we said the pattern here was 2n squared to see how many electrons something can hold. So now it becomes an issue of, well, how many electrons are in each orbital in each atom? And it's just based on the numbers at the top. As an orbital gets filled, or as its subshell gets filled, it moves on to the next one. Right? And it follows this order here. So we'll go from 1s, once that's filled, kind of loops around, fills the 2s orbital. That's where the next electrons go. After that's full, electrons start filling the 2p orbital, then the 3s orbital. So this is the order that they're added to. All right, as atoms get bigger, more electrons come in. A couple of key things to note are these arrows. We're going to represent electrons as up arrows or down arrows. So if an arrow is pointing up, it means it's spinning clockwise, right? That's just describing the magnetic and electrical fields of the electrons. And a down arrow is talking about the counterclockwise spin, so the opposite of an up arrow. So we're going to use this pattern, and again, this is the order that electrons get filled in, to look at some atoms here. So we're going to start off with sodium. So sodium has 11 electrons, and that's based on its atomic number, whereas nitrogen has 7 total electrons, not just valent. So if there's 11 protons in this nucleus, that means there are 11 electrons outside of it. So based on the pattern that we saw here, the first orbit to get electrons is the 1s orbital. So the way we draw this is we have one electron going up, I'm going to use half arrows here, and one electron going down. They always have opposite spins when they're in the same sublevel. Okay, so there's a couple of annotations. The number tells us the energy level. The letter tells us the orbital. And this tells us the subshell. So that's like px, py, and pz. Right, so for 2p, that's px, pz, and py, because we had said those had values of 1, 0, and -1. So that's what the annotation is describing. So of our 11, the first two go in the 1s orbital. The next two electrons, they're going to be attracted to the nucleus as close as they can. And we look at the energy here. So the 2s orbital is the next lowest energy. That's where the next two electrons will go. Okay, so they'll start at the bottom here. And again, they're opposite spinning. They always pair up in opposites. Right? We never have two of the same direction electron beside each other. That would create destructive interference, and the electrons would become unstable. So we've put 4 of our 11 electrons into their orbitals. Now we're going to see where the next 7 are. So in the p orbital here, you can see that there are 3 spots, and if each spot can hold 2, because those are like the lobes of the orbitals, okay, this p orbital can hold 6 electrons. Now there's an order that it gets filled. So imagine living in a house, okay, with 3 rooms. Right? If there were 5 people in the family, right, we wouldn't put all 5 people in one room and leave the others empty. That wouldn't make sense. What we would most likely do is try to evenly divide up the rooms, which I'm not going to be able to do completely, but oof, that made it even worse. Here, let's try this. Splitting that into 3 different shapes here. One. It's not completely even, but that's okay. We'll go with it. I'm going to come back to my square analogy here, just to stay consistent. Okay, so instead, what you would do is you would give each person their own room first, and then you would start doubling up after everyone has their own room. And that's what electrons do. The lobes are like their room. So in the 2p orbital, back down here, I have 3 rooms, but I have 7 electrons left. I've used 4 of the 11. So I'll put 1 in each lobe, or each subshell, and now I'll go back and fill them so that nobody's doubled up, right, with something else empty. You would never see the orbitals like this. All right, that is incorrect because they're not evenly spread out, and that's part of the guidelines that we're going to follow. So that's not right. Now we've placed 10 electrons total. If you count each arrow as 1 electron, there's 1 left over, and it goes in to the 3s orbital. So again, if you're following this template, they're all arranged in order already, but this order is based off of the staircase pattern over here. Okay, so again, it's telling us what order to get filled in, and it's being ranked by energy at this point. Okay, so that's this one completed. All 11 electrons, there's 11 arrows, right, are placed in here. And if you look, the valence electron is 1, and sodium has 1 valence electron. Okay, so now's a good time to pause, either rewatch it and try nitrogen on your own. Okay, so hopefully you do pause it, and I'll go forward from here now. So you've seen that nitrogen has 7 electrons, so it has 7 protons. We're going to fill the energy levels in order. So 1, 2, 3, 4. Now, when there's more than one lobe, like there are here, we have the P, X, Y, and Z, right? Fill each one once first. So we put 1, 2, 3, 4 electrons down first, 5, 6, 7. It's convention to use the up arrow first and then the down one after that. So that's it. We've run out of electrons. They're filled. Okay, now if I draw the Lewis diagram for nitrogen, okay, based on its 7 valence electrons, 7 electrons, it has 5 valence. You can see that there's an electron pair and 3 single electrons, but there's 5 in total. So the valence shell is the highest energy level, which is 2 here. So the second energy level is the valence. There are 5 electrons in this level. Now, hopefully you can see with the 2s orbital, see how there's 2 electrons paired up here? That corresponds to the lone pair. And the reason for that is they're stable. So they're less reactive than these individual electrons. So what's going to happen is when an atom goes to react and share electrons, it looks for these unfilled orbitals to accept electrons in. If they're all filled, it goes up to the next orbital, right? And it depends on the stability of the atom at that point. So that's what we talk about overlapping orbitals to share electrons, all right? And keep in mind, this isn't what an atom looks like. An atom looks like if it has a 1s orbital, it's got that small sphere in the middle of it, bigger sphere on the outside, and then it has the p orbitals, which look like this. And you have that one pointing kind of in 3D. That's what a nitrogen atom looks like. And for there, you have 1, 2, 3, 4, 5, 6. If each p orbital can hold 2 electrons, they only have 1 each in that case. The inner orbital has 2, and the outer s orbital has 2. So altogether, there should be 7. And there is, and these ones, we'll just scratch those out. So that's really what an atom looks like, right? But there's no borders there. The electrons just move in those patterns. Okay, so what we did was follow these rules, all right? We started with the lowest energy level first, which was 1s, then 2s, 2p, and we followed the staircase pattern to tell us what order to add electrons in. Then, the second theory that we followed was Hund's rule. Whenever electrons are added to the orbitals with the same energy level, each orbital must receive 1 electron before pairing. That's the idea of getting your own room before you have to share. Okay? And they must all have the same spin. So you can't do this. If we have these 3 here, I can't go 1, 2, and 3. That's incorrect. This is incorrect. That is really incorrect, because 2 electrons can't have the same spin. And then lastly, that is correct here, like with what we did for nitrogen. Okay, so that's Hund's rule. 1 electron per orbital until they're all half filled. The last theory based on this diagram is the Pauli exclusion principle, and that's the idea that no 2 electrons can have the same 4 quantum numbers. That means they have to have opposite spins. So if I take a 1s electron, one's up and one's down, and I write their quantum numbers for it. So I have electron A and electron B. Electron A is in the first energy level, the s orbital, so its L value is 0. That makes the ML value 0. And it's pointing up, so it has a positive 1/2 spin, which means clockwise. Now, no 2 electrons can have the same sets of numbers. So what that means, electron B, if you look at it, it's in the first energy level, in the s orbital, which means it moves in 3 dimensions. It can't be spinning clockwise, it has to spin anti-clockwise or counterclockwise, again, to avoid destructive interference. So that is what that's describing. In the orbitals, the arrows have to point the opposite way. Okay. So let's look at the energy level diagrams for ions. So have your periodic table out and look up zinc and how many electrons it has. Okay, hopefully you pause and do that. And when you come back, you'll notice that there are 30 electrons in zinc. The zinc ion, so we have Zn and Zn2+, which means it's lost 2 electrons. So it should only have 28 electrons. So let's do zinc on the left and zinc ion on the right. We have 30 electrons to place. And what we're trying to see is where are the valence electrons in zinc? So we're going to start counting. 1, 2. And feel free to pause and try this for yourself and then double check. Okay, I'm going to go through and assume you've tried it or you're just checking to see the process. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Notice how I filled 3s completely because it's lower than 3p. 3s only has one lobe. 6, 8, 10, 12, 13, 14, 15. So we're officially half filled, right? We've used 15 at this point. Okay, we split them up evenly. They have the same spin. 16, 17, 18. Okay, so we've filled with that. Just making a note for myself. Now I have 4s over here and 3d. So to know which one I fill, I look based on the energy. Okay, so we fill the lowest energy orbital first. 19, 20, 21, 2, 23, 4, 5, 6, 7, 8, 9, and 30. All right, so that's zinc. Now, the zinc ion, you can do the same thing, right? You have 28 electrons, but what you have to consider is where those electrons are lost. So what we're going to do is we're going to circle, you can try this yourself, circle the valence orbital here. And again, pause and try that. Now, if you did try it, you would have been choosing between 4s and 3d. The 4s orbital is the valence orbital, okay, because valence is determined by the number, not the energy. A 3d orbital has more energy than a 4s orbital, even though it's closer to the nucleus, because there are more electrons interfering with each other. There's more repulsion happening. There's only 2 in the 4s orbital, but they're farther away, which means they're more likely to break away from the nucleus's attractive force. So again, the staircase pattern dictates the energy, not the distance. This is not distance. And the valence shell is based on the distance. So if I go back to zinc, and I have to take away 2 electrons, okay, from 3d or 4s, I take them all from 4s, because that's the valence shell. And I know I'm just going to recopy this because I know none of these electrons are touched. They're all the same. Okay. And I'd leave it like this. So this is a total of 28 electrons. And we've lost the valence electrons from the 4s orbital. So we look at the highest energy level electrons. Now, if there were electrons in the 4p orbital and the 4s orbital, then we would take them from the 4p because they're both in the valence shell. Okay. So it's similar to a Bohr diagram's process, but again, the farthest electrons, the outermost, are the ones that are lost when ions form or reactions happen, because reactions form ions, right? And those ions stabilize each other. So rewatch that if you need to, and then there's lots of practice questions to go with it. Okay, there's a couple of exceptions to go through. We accounted for the number of electrons before we filled the energy levels because we don't fill it in order in this case. Okay, and we're just going to say gain or lose from valence. And the valence is the highest energy level, which is your N value. So there's a couple of rules, and they involve the transition metals. And one major rule is bolded here. You'll see this one often if you continue in chemistry. Whenever the d orbital has 4 or 9 electrons in it, so what that looks like is the d orbital has 5 lobes. 1, 2, 3, 4, or 1, 2, 3, 4, 5, 9. Now I did that because I knew there was only going to be one left over. Normally you should fill them one at a time. So the orbitals are stable when they're half full. All right, and the atom will force itself to rearrange, and what it does is it takes one electron from an s orbital So if I have an s orbital down here and a d orbital down here, okay, we're skipping the p orbital, so that would have to be full, right? It takes one of those electrons and promotes it because it's easier for it to do that than to leave it with one short of a full octet. There's more balance of energy this way, okay, without having studied energy. And it results in more stable atoms, which they do by themselves. We can't stop them from doing that. So we'll look at two examples here. We've got chromium, which is Cr, and it has 24 electrons, and copper, which is Cu, has 29 electrons. So if we draw these normally, and you're welcome to pause and try this yourself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. Okay, so look, there are 4 electrons in the d orbital. This is unstable at this point. It really wants to be half full. So what it does is it's going to grab this 4s electron because it's closest in energy to it. I'll explain that in a second. Okay, the p orbital is too far down. Those electrons wouldn't be able to sustain that energy. Okay, it'd be like moving into a neighborhood you cannot afford. You can do it for a short amount of time, right? But eventually you would run out of money. The electrons have to make similar energy level jumps or they'll just fall back down. So the s orbital is close enough to the d orbital that it becomes stable. Now what happens is, I'm just going to erase this. There's 1 electron left there, and a new one gets promoted here. So this automatically happens. And look at that. Now we've got a half-empty s orbital, which is more stable than a half-empty d orbital. Right, we'll make a note of that. So it's all based on choice. Would I rather be unstable or more stable? And the atom always chooses stability. So for copper, you can try this yourself. It's the same diagram, but with 5 more electrons. So let's get back up to that point. Okay, we're just going to add these all in as if we were there. Then we're going to double up until we get to 29 electrons. So I just added 5 to what was my original diagram there. So notice how there's 9 here, 9 electrons in the d orbital. That's not as stable as if it takes one and it leaves the s orbital half empty. So the atom can live with that. It can live with an unstable s orbital. It cannot, maybe I'll try to change a different color here. It cannot live with an unstable d orbital. It's too high energy for that. Okay, I'm just going to change my pen back to red here. So that's what happens. The atom rearranges itself whenever the d orbital ends in 4 or 9 electrons. So it's something to pay attention for. All right, it's an exception. And that breaks the rule, the Aufbau principle, obviously, but it results in a more stable atom, which is why it happens. So we're going to stop at that point here. We're going to call this part 1, and we'll do electron configurations in a part 2 video. Hopefully this helps you clear things up a bit.